So we'll finish up section 2.8 and state one more result concerning boundedness of linear operators. And then we'll shift over to some things that are a little more geometric. Theorem 2.32 states that a linear operator T mapping normed linear space X to normed linear space Y, where Y is finite dimensional, is bounded if and only if the null space of T, N of T, is closed. So this time we're mapping into a finite dimensional space. Quick observation, for example, the previous result, part A said we have a linear operator T mapping X to Z, where the domain is finite dimensional, and that implied boundedness. So this current result differs from the previous in that this time we're looking at the codomain and saying it's finite dimensional, and this requires apparently a consideration of the null space. So proof of that is as follows. Okay, if and only if claim, so T maps X to Y, Y is finite dimensional as a setting, and it's related to the closedness of the null space. So first, let's assume T is bounded, and then we need to show that the null space of T is closed. So assuming T is bounded, bounded linear operators are continuous. Proposition 2.6, in fact, they're uniformly continuous. By now, somewhat of a familiar idea. The null space of T is the inverse image of the closed set consisting of only the zero vector in normed linear space Y. Inverse image of T. Not that T is necessarily invertible. We can still talk inverse images, that old story. Now, continuous mappings have inverse images of closed sets as closed sets. We discussed this in senior level analysis. There's a link to some notes. It comes to you probably first that inverse images of open sets are open, but inverse images of closed sets are closed as well. Might need to deal with some relative open and relative closed in certain settings. But the inverse image of this closed set is closed. That is, the null space of T is closed, and there you go. So the continuity simply gives us that the null space is closed. Quick observation, we didn't use the finite dimensional hypothesis on Y. We didn't use that in this first part. So this actually holds in a more general setting. Second, suppose the null space is closed, and now we want to show that T is bounded. Consider the quotient space, X mod, null space of T, X mod N of T, and the mapping T tilde, mapping the quotient space into Y, defined as T tilde of X bar equals T of X. Okay, X bar is the equivalence class containing X in the quotient space. We actually dealt with this same idea in section 2.7. And we're making a claim now, and we'll justify it from 2.7, that thusly defined T tilde is 1-to-1, is injective. Let's go back to 2.7 and check that out real quick. So here we are in 2.7, exactly the same thing we had. There's no assumptions of finite dimensionality here, but we've got finite dimensionality of the Y. Simply a linear operator from X to Y, null space is N of T. Consider the quotient space and define T tilde on that quotient space to map equivalence class X bar to T of X. And we've given a little one-line argument that such T tilde is 1-to-1. So a note from the previous section justifies the 1-to-1-ness there. Here's why we need the 1-to-1-ness. Y is hypothesized to be finite dimensional. Then it must be that the quotient space is finite dimensional. We couldn't map an infinite dimensional space 1-to-1 to a finite dimensional space. Now, they could potentially be the same cardinality, but think how the bases are mapped. We'd have to map the basis of one to one on the basis of the other. That couldn't be done if we had an infinite dimensional quotient space mapped to a finite dimensional space Y. So it must be that X mod n of t, that the quotient space is finite dimensional. And then we have t tilde mapping a finite dimensional space into a normed linear space, which by the way is also finite dimensional. Theorem 2.31 part A that we just looked at showed us that that implies boundedness. So if the codomain is bounded, if the codomain is finite dimensional, then such a linear operator is bounded. So that gives us that t tilde is bounded. We're not interested ultimately in t tilde. We're interested in operator t being bounded. So we're getting closer. We have a relationship between t tilde and t as given here. So t tilde is bounded. T tilde is defined as t tilde of x bar equals t of x. Next slide, we'll use that information to observe that t can be written as t tilde composed with the canonical projection pi sub n of t. Recall pi sub n of t takes space x, maps it into the quotient space. It simply projects an element of this space onto the equivalence class containing it by taking, say, x and mapping it to x bar. So if we were to apply t tilde composed with the canonical projection, apply that to x, the canonical projection would take x and map it to x bar, and t tilde of x bar was by definition t of x, as we saw in the previous slide. So these two maps do the same thing to all elements of normed linear space capital X. So we've got this composition. We know t tilde is bounded. That we showed on the previous slide. The norm of the canonical projection was shown to be 1. We showed this in Theorem 2.27 part C. So proposition 2.8 tells us that the norm of a composition of operators is less than or equal to the product of the norms. Proposition 2.8, it's been a while since we've seen that. But the norm of the composition is less than or equal to the product of the norms. That was proposition 2.8. So the norm of t, which is the same as the norm of t tilde composed with the canonical projection, is less than or equal to the product of those norms. We just saw that the norm of the canonical projection is 1. We get a 1 there. So we get the norm of t is less than or equal to the norm of t tilde. T tilde is bounded from the previous slide, so t itself must be bounded. And there's the other part. So as stated, there's some properties of linear operators in terms of boundedness and finite dimensionality and how those things interact. So we're shifting gears a little bit now. And we'd like to talk about orthogonality. We'd like to talk about perpendicular vectors or vectors perpendicular to spaces. You do a lot of that in linear algebra when considering bases, when you go through the Gram-Schmidt process. You consider often collections of vectors perpendicular to subspaces, to spans of other sets of vectors. And we're going to try to address something like that. Problem is, we're in a normed linear space. We don't have an inner product necessarily. We don't have a dot product. We can't measure angles. That's why you want dot products. You can measure angles between vectors if you have a dot product or an inner product. Before we're done, we'll certainly consider inner product spaces. A complete inner product space is called a Hilbert space. And the beauty of those spaces are geometrically, they're a bunch like Rn. But we're currently in a normed linear space, and we don't have a concept of dot product, and so we don't have a concept of angles. But based on our experience in Rn, we will make the following definition concerning vectors perpendicular to subspaces in the setting of a normed linear space. So this entirely has to be done with a concept of norm and no concept of dot product. The definition is, given a proper subspace, capital M, of normed linear space X, a non-zero vector in space X is said to be perpendicular to subspace capital M if the distance from X to M, which recall, here's the definition of the distance between a vector X and a set M. So definition in this equality, if this quantity equals the norm of X, then X is said to be perpendicular to M. So we've defined perpendicular with no concept of inner product and no concept of angles, but taking our inspiration from the little figure below. So the idea is, here's a little subspace. I think of it as a plane, like a two-dimensional subspace of Rn. Put all those vectors in standard positions and they'll determine a plane. Here's vector X perpendicular to this plane. So let's take Y, an arbitrary element of M. So here's a vector Y. And what we're going to do is measure the norm of X minus Y. Norm of X minus Y would be this vector in red here. We would have these be perpendicular if the infimum of all of these norms equals the norm of X. In the little picture here, really an illustration from R3, schematically valid maybe for Rn, but anyhow, we could make the red vector and the black vector, the X minus Y vector and the X vector respectively, we can make those have the same norm simply by taking in the picture the Y vector equal to the zero vector. So we take zero vector here in the picture, and we'd have these two coinciding, and then you would have the distance of vector X to M equaling the norm of X. You might kind of think in terms of points. In some sense, we might have a plane down here associated with all vectors in some two-dimensional subspace in standard position. We put vector X in standard position, then that determines the point up here at the head of that vector. How far is that vector, the point at the head of vector X, how far is it from M? Well, it'll just be that straight line distance, if such a vector X actually exists. And that makes geometric sense as well. You'd simply measure the distance from the point down to this subspace. You take the straight line distance down here to the tail of the vector, which again, by the way, if these vectors are in standard position, would correspond to Y being the zero vector in this picture. So there's our definition of perpendicular. It's not a definition of perpendicular vectors, but of a vector perpendicular to a subspace, though we could probably tweak it and talk about vectors being perpendicular in normed linear spaces. Simply take a vector and take its span. There's a subspace. So we could talk about a one-dimensional subspace and translate this into other settings. But there's what we get for our definition of perpendicular in a normed linear space. I would really prefer to mostly hold a conversation of perpendicular until we have an inner product. And then we get all the geometry of Rn in inner product spaces. This story here is sometimes there's not perpendiculars to a proper subspace. This is to be shown in one of the exercises. So in the setting of normed linear spaces, maybe we don't have perpendiculars to subspaces. That won't be the situation in inner product spaces, at least in complete inner product spaces and Hilbert spaces. But there's always nearly perpendiculars to a subspace M, and that's what Riesz's theorem states. This is given a closed proper subspace M of a normed linear space X, and given epsilon greater than 0, there's a unit vector, X, such that the distance from X to M is greater than or equal to 1 minus epsilon. Unit vector, X, so the norm of X is simply 1. Well, maybe we can't get this distance to equal 1, but we can get it close to 1, is the claim of Riesz's lemma. So let's go through a proof of that. All right, so we'll take epsilon to be greater than 0 and sufficiently small. So take it to be less than 1. Somewhere down the road, we're going to consider the quantity 1 minus epsilon. We'll need that to be positive. So take epsilon positive and sufficiently small. Let y be a vector in the linear space that's not an M. It says M is a proper subspace of the normed linear space, so there are such vectors. So take y to be in the normed linear space, but not in the subspace, capital M, and define R to be the distance from vector y to subspace M. M is closed. Closed. There's the hypothesis on that. So it must be that R is greater than 0. I could, without this assumption of closed, I think we've seen examples of this, we could have a vector be distance 0 from a set and yet the vector not be in the set. So that can happen certainly in metric spaces, but not when the set's closed. What would happen then is if the distance is 0, it must be either that y is in this set or y is a limit point of this set. So if M is closed and y is not in that set, then that distance must be positive. The distance from y to M is defined as an infimum of the norm of y minus M, as M ranges over subspace capital M. So, definition of infimum, there exists a z in M such that the norm of y minus z is less than or equal to r over 1 minus epsilon. So the distance itself, r equals the distance itself, r equals this infimum. What we've done here is looked at a parameter a little bit bigger than r divided by 1 minus epsilon, well, that's strictly greater than r. 1 minus epsilon is strictly less than 1. We've divided by it. We've actually produced something bigger than r by considering this quantity. Remember, r is the infimum, so if we go a little bit bigger than r, we can find specific vectors in capital M, such that the norm of the difference is less than or equal to that parameter that's strictly greater than r, the property of infimums. Call that vector z in this case. So there does exist such a z from the definition of infimum that satisfies this property. Now, if we take any vector v in M, we're trying to look at a distance here, so we're taking an arbitrary vector in M. We have that z plus v is an M. Z was a particular vector. Here we've chosen an arbitrary vector. Both of them are in subspace M. So their sum is in subspace M. It's closed under vector addition. So if we look at the norm of vector y, this given vector from above, minus vector z plus v, some vector in capital M, we know in norm this will be greater than or equal to r, because when we take the infimum over all such vectors in capital M, we get r out. This is a particular vector in capital M, so we must get r or greater out from this norm. So if we take the distance from y minus z to M, that's greater than or equal to r. So what we do is associate the y and the z and then let v range over M, right? It was an arbitrary vector over here. This norm for any vector v in M is greater than or equal to r. So when we take an infimum, the distance we'd be computing then is also greater than or equal to r. And by our choice up here of norm of y minus z is less than or equal to r divided by 1 minus epsilon. Cross multiply, that will imply that r is greater than or equal to the norm times the 1 minus epsilon, and that's what we've stated here. So we've got the distance, y minus z to m, greater than or equal to 1 minus epsilon, norm of y minus z. How we doing? We're looking for a vector x, a unit vector x that satisfies this condition here. Well, this looks pretty good. We've got the 1 minus epsilon here. We've got a distance related to a vector and subspace M. Here it's the vector y minus z. We want x to be a unit vector. All right, let's take this y minus z and normalize it. So define x to be y minus z divided by its norm. So that normalizes that vector, creates a unit vector. X is a unit vector, and B, arithmetic balances. The distance from x to m, that is the distance from, we define x to be y minus z normalized to m, equals little property of distances in this setting. If we take the distance from vector alpha w to m, that equals the absolute value of alpha, or modulus of alpha, times the distance from w to m, we're claiming in passing. It follows from the scalar property of norms. Scalars come out of norms and absolute value, so it follows from that. So we can take this constant 1 over the norm of y minus z, bring it outside with an equality. Don't need absolute values because it's already non-negative. And we're left then with a distance from y minus z to m. We were just talking about the distance from y minus z to m. So we've got the 1 over the norm. There that is. Distance from y minus z to m. We saw that's greater than or equal to 1 minus epsilon times that norm. Greater than or equal to 1 minus epsilon times that norm. That norm cancels with this norm to leave us with 1 minus epsilon. And that's what we were looking for. We were looking for x, a unit vector. X is a unit vector, such that the distance from x to m was greater than or equal to 1 minus epsilon for a given epsilon. So, Riesz's lemma, in itself, possibly not terribly interesting. We're going to use it for something a little more interesting. We've claimed in one of the exercises that perpendiculars maybe don't exist. Riesz's lemma tells you you can get in a normed linear space as close as you want positive to having perpendiculars to proper subspaces. So that does have some geometric flavor to it, but not as much as Riesz's theorem. So the following result is particularly intriguing. It relates the algebraic idea of dimension to the topological idea of compactness. It also hints at the fact that the Heine-Borel theorem only holds in finite dimensional spaces. All right. Riesz's theorem says a normed linear space X is finite dimensional if and only if the closed unit ball is compact. So take that, Heine-Borel. Heine-Borel would tell you a closed and bounded set. This is certainly a closed and bounded set. Heine-Borel would say closed and bounded sets of real numbers or closed and bounded sets in Rn are compact if and only if they're closed and bounded. Let me try that again. A set is compact if and only if it's closed and bounded, Heine-Borel says, in R or Rn. Well, here's where Heine-Borel fails. In infinite dimensions, here's a closed and bounded set that's not compact. So there's specifically where Heine-Borel fails. Heine-Borel fails in infinite dimensional spaces. And now for the proof. So the statement is formally a normed linear space X is finite dimensional if and only if the closed unit ball B bar 0, 1 is compact. So 2 claims. First, let's suppose X is infinite dimensional. we're actually showing the contrapositive of one of the cases. We're going to create a sequence of unit vectors, x sub n, using Riesz's lemma as follows. Take x1 to be any unit vector in the norm linear space. Then we're going to do this inductively with n vectors chosen. Choose a new vector, an n plus first vector, by defining the span of those first n vectors to be m sub n. So this would be a subspace of the norm linear space, be a proper subspace, because this is dimension at most n, and we're dealing with an infinite dimensional norm linear space X. So M sub n is a finite dimensional subspace of the norm linear space X. We saw in the third part of Theorem 2.31 that finite dimensional subspaces are necessarily closed, so we get closure of M sub n. And of course, M sub n is not equal to the whole norm linear space because it's finite dimensional and the whole norm linear space is infinite dimensional. Riesz's lemma required a proper closed subspace, and that's what M sub n is. So we know there exists a unit vector x sub n plus 1 that's nearly perpendicular to the subspace M sub n. So we're going to take epsilon equal to a half. So we just fix epsilon at that. Riesz's lemma allowed us to use any value of epsilon. We're going to use epsilon equals a half. And we know there's a unit vector x sub n plus 1 such that the distance from x sub n plus 1 to m sub n is greater than or equal to 1 minus a half, 1 minus epsilon. So greater than or equal to, say, a half. So recursively defining the sequence, it has the property that any two elements in the sequence are at least distance 1/2 apart. We make this new vector x sub n plus 1 at least distance 1/2 from all of the previous vectors in the sequence. They're all contained in this proper subspace. So every time we add a new vector, it's, in this sense, it's distance at least a half from all of the previous vectors. So when we create the infinite sequence, then any two elements in that sequence are distance half apart. And you can't do that in finite dimensions in terms of unit vectors. So we can't have this sequence having some sort of convergent subsequence. The terms are always half apart. Let epsilon be less than a half. You can't get a convergent subsequence from this. Can't be a convergent subsequence. X sub n, these were all chosen to be unit vectors, so they're a subset of the closed unit ball. So we've got a sequence in this set that has no convergent subsequence. That is, this set, B bar 0, 1, closed unit ball, is not sequentially compact, kind of our second version of the definition of compact. Not sequentially compact, it's not compact. So what we've shown, if infinite dimensional norm linear space, then closed unit ball is not compact. Let's unwind that contrapositive wise. That is, if the closed unit ball is compact, then the space must be finite dimensional. So we've got that implication. If closed unit ball is compact, then norm linear space is finite dimensional. We need to show that if the space is finite dimensional, then the closed unit ball is compact. So secondly, suppose X is finite dimensional. Then by Theorem 2.31 part B, we know all norms on a finite dimensional space are equivalent. So put your favorite norm on norm linear space X. If we were given this particular norm, we can replace it with a suit norm. That'll be an equivalent norm. In particular, properties like closed will be the same no matter what norm we use. Boundedness will be the same. The bound might be different, but the boundedness will be the same. Sets which are bounded with respect to one norm are bounded with respect to another. So closed and bounded are preserved if we shift this over to a, say, a soup norm. The fundamental theorem of finite dimensional vector spaces, a little link there to some linear algebra notes, and we'll discuss this more before this class is over as well. And we'll have a fundamental theorem of infinite dimensional vector spaces, as I call it. Tells us that all n-dimensional vector spaces over a given scalar field are isomorphic. So the norm linear space we're dealing with is a vector space, is isomorphic to, say, the space BF, bounded functions on set F, where we took set F to be the set consisting of the elements 1 through n. We need the dimensions to be the same. The dimension of BF is the parameter n, so we'll take n to be the dimension of X. And then these two spaces have the same dimension, and so they're isomorphic. Now we know that the closed unit ball is closed and bounded, and we've shown specifically in Theorem 2.29 that the closed unit ball is compact in the normed linear space B of F, bounded functions on set F, and so we get that the closed unit ball through the isomorphism is also compact in normed linear space X. So if the space is finite dimensional, then the closed unit ball is compact as claimed. And that takes care of section 2.8 and these little topological ideas. Next section, we'll look at LP spaces and just have a whole pile of various definitions and results, mostly without proofs. We're not assuming a measure theory background or Lebesgue integration background, and that doesn't come at great expense, but it's in the next section. We'll have to go through and just lay out a bunch of definitions without justification because we're not assuming that background. So I'll see you in section 2.9 here shortly. Have a nice day.